In this presentation, I will talk about refined trigonometric shear deformation plate theory based on neutral surface position is proposed for static analysis of FGM plate. I start by explaining the purpose of this work. The objective of this study is to develop a new hyperbolic shear deformation theory based on neutral surface position for static analysis of FGM plate. In this presentation, I will follow the following plan. I start by introducing generality of function gradient material by discussing their definition, property, and reliability. Then I move on to the different theory of plate. I focus in the third part on analytic study of FGM plate based on neutral surface position. The fourth part presents the comparison of results and their validation. In the fifth chapter, I expose the result and the discussion. I conclude my presentation by quoting the general conclusion and perspective. Generality of functional gradient materials, local optimization of propriety, for example by combining a material of high hardness with the surface of tenacious materials, then pose of the problem of the interface. The student transition of material propriety through the interface between discrete materials can result in high stress concentration that load the plastic deformation or cracking, as in the case with conventional composite non-FGM. So the solution of continuous transition of property solved by a composition gradient reduce their harmful effect with the use of property gradient materials FGM. What is this material of FGM? FGM is a non-homogeneous composite mode from different phases of material constituting usually ceramic and metals. This is due to the fact that FGM and ceramic constituents are able to withstand high temperature environment due to their best thermal resistant characteristic, while metal components offer strong mechanical performance and reduce the possibility of catastrophic failure. Global FGM achieve the multi-structural status of their property gradation by gradually varying the density fraction of the constituent materials. Their materials property exhibit a continuous and smooth variation from one surface to another, eliminating interface problem and reducing thermal stress concentration. I end this chapter by presenting the various possibility laws that are used to describe the values in the materials property of FGM material according to the thickness of the plate, power law function PFGM, sigmoid function SFGM, exponential function FGM. The different theory of plate in order to solve the problem of structure having as structure element beams and FGM plate in the elastic region. It is necessary to choose the correct theory which correctly describes the static behavior of the structure and the resolution method to be applied. For an analytic resolution, we have several theories were proposed. So for the thin plate, we have a classical theory of plate of Love-Kirchhoff. This theory we do take into account the shear effect. Therefore, the deformation due to shear is negligible. For thin plate, we have taking into account the shear effect. I have first order shear deformation FSDT of middle resonance. No shear correction factor are required. High order theory, 5 or more variable HSDT of ready to radical, and raffinate theory, 4 variable similarity with the CPT, no correction factor, satisfy the boundary condition. Analytic study of FGM plate based on neutral surface position. The interest of this chapter is to present a new hyperbolic shear deformation theory of FGM plate based on the position of neutral surface. The FG plate is made from a mixture of ceramic and metal, and the properties are assumed of vary through the thickness of the plate. The specific position of neutral surface of FG plate to different planes are considered for the measurement of Z, normally ZNMs and ZNS, measured from the midline surface and neutral surface of the plate, respectively, as indicated in the figure A. The volume fraction of ceramic vessel is expressed based on ZNMs and ZNS coordinate as the position of neutral surface can be obtained hypothesis of the raffined new theory. Transverse displacement W include two components: displacement WB due to bending and displacement WS due to shear. We have an effect every extension plus bending plus shear. The axial displacement U and V in direction X and Y respectively. The bending component UV and VB are assumed to similar to the displacement given by the classical plate theory. Therefore, the expression for UV and VB can be given as the shear component are the displacement field to the deformation field with shear stress. For elastic and isotrope FGM, the constitutive relation can be written as here are the stress equation deformation according to engineering constitutive. Virtual work applied to determine equilibrium equation and variation of the virtual work of the internal and external effort are given by the following formula. Comparison and validation of results. In this chapter, the occurrence of the solution presented is verified by comparing the result obtained with existing solution. In the first table, we have different comparative results between high order shear theory and the new raffined theory. We note that the value adopted by the new theory are similar by contribution to the other theories ZSDT and HSDT. For the second table, it is the result obtained at the effect of volume fraction exponent on the dimensional stress of FGM square plate subjected to sinusoidal loading for different power index value. Result and discussion. On this last chapter, I focused on the analysis and interpretation of various results obtained as a result of non-dimensional deflection and stress, respectively. So the first figure shows non-dimensionalized central deflection W versus power law index N for a simple supported square FGM plate under sinusoidal load. We notice the rho increase when the power law index increase. For figure 2 and figure 3, the central deflection was plotted W as a function of the side of thickness ratio A divided H and A divided B of FGM square plate. in figure 3 show that the deflection is maximum of the metal plate and minimum of a ceramic plate. The figure 4 and the figure 5 show the distribution of longitudinal stress in the plane through the plate shift. We can also say from the figure 4 and 5 that the normal stress sigma x and sigma y are compressive through the plate up to z equal 0.149 and then they become tensile. In the figure 6 show the variation of in-plane shear stress through the thickness of an FGM plate for different value of say the thickness ratio A divided H. It is noted that the maximum value of the stress and the shear stress in the 2xy plane occur on the top and the bottom surface of the plate. In the figure 7 and the figure 8 show the variation of transverse shear stress through the thickness of an FGM plate for different value of aspect ratio A divided B. This distinction between the curve in the figure 8 and the figure 9 is the figure 7 and 8 of use as strain gradient increase the inhomogeneity play a greater role in stress distribution calculation through the thickness distribution of the shear stress 2yz and 2xz are not parabolic and the stress increase at the aspect ratio. It is to be noted that the maximum value occurs at z equal 0.2, not at the plate center as in the homogeneous case. General conclusion and perspective: the displacement and adimensional stress obtained using raffinate theory, wildcard inconnu, are almost identical, while the displacement and stress proved by other shear deformation while sink inconnu. The deflection is maximum for a metal plate and minimum for a ceramic plate. The normal stress of a ceramic plate are the same as those of a solid metal plate, that is, the plate is completely homogeneous. The maximum value of this stress, longitudinal stress, as well as the shear stress to xy, the plane, occur on the top and the bottom surface of the plate. When stress gradient increase, homogeneous play a greater role in stress distribution calculation.